So, Hess's law is something that we are introduced to at A level, and I think it's fascinating. And it only makes sense really if you have a good grasp of, or no, let me rephrase that. It can make more sense if you have a good grasp of vectors, which is a mathsy topic. So if you find Hess's law and Born-Haber cycles, which you do in year 13, if you find them hard to get your head around on how it works and why it works, and therefore applying it to new situations you find difficult or a bit of a challenge, see if you can refresh your memory on what a vector is and how vector quantities work in terms of working out the differences between points using vectors, etc., because that might help. Anyway, we're not going to do that today. We're going to think about Hess's law. Hess's law states the enthalpy change for a chemical reaction is the same whatever route is taken from reactants to products. Again, you'll find different definitions of Hess's law all over the internet. The principle is the same. It just says the enthalpy change for a process is independent of the route taken. What that means is it doesn't matter how you get from A to B, the difference between A and B will stay the same. It doesn't matter if you've gone all around the houses to get from A to B, the difference between A and B is the same. You could go straight there, fine. You could go all the way around here, fine. The difference between A and B is the same. It's not asking you for the route, it's asking for the difference between the two. Okay, so for example, if we're going to have a look at what they called a Hess cycle here, we've started with A and B. The enthalpy change to get from A and B to C and D is delta H1. So it's the enthalpy change number 1 to get from A and B to C and D. But for some reason, perhaps, maybe it's too complicated a process, maybe I don't have the laboratory equipment, whatever reason it is, maybe it's not possible to measure. I don't know, I can't measure the enthalpy change to go from A and B to C and D. So I'm going to work out the enthalpy change going a different way that starts at A and B and finishes at C and D and work out what that enthalpy change is. I'm going to go via E and F, which means there is an enthalpy change from A and B to E and F, which I'm going to call delta H2. And there's an enthalpy change from E and F to C and D, which I'm going to call enthalpy change 3. Notice the direction of the arrows. This is another place where I would highly recommend you understand what is happening and how they're constructed, and don't just memorize Hess cycles, because you'll find it really difficult when you come across a complicated one or one in a context you're not used to. One of the key ways of understanding Hess cycles is by understanding what the arrows represent. Every time you see an arrow in a reaction, it's telling you the progress of the reaction. It's telling you what the reactants are and what the products are, what you've started with and what you're ending with. So the direction of an arrow is important because that's telling you the direction. And we know, hopefully, from thinking about energetics, that a forwards reaction, if a forwards reaction is exothermic, the backwards reaction will be endothermic to the same degree. The amount of energy needed that is released going forwards with an exothermic reaction is the same amount of energy that's taken in on the reverse in the endothermic direction. So one value is, so the forwards reaction in this case will be negative, a negative enthalpy change. The backwards reaction will be positive. And that's really important, that one is positive and one is negative. So you have to make sure you've got your arrows facing the right way. You must make sure your arrow is representing the process that number is representing. So here I've got my arrow going down and my arrow going up. That means that if I wanted to go from A and B to C and D, so if I wanted to work out what delta H1 was, I could add delta H2 to delta H3, and I would get delta H1. In this case, if I want to go from A and B to C and D, I'm going with the process of A and B. So whatever the value for delta H2 is, I can then add it to whatever the value for delta H3 is, and I will get that process. But usually there's a slightly confusing thing where the arrows tend to point in the same direction. So they both tend to point down or they both tend to point up. Not always, but that does add a little bit of a complication. So let's have a look at an example. If we look at calculating enthalpy changes of combustion or enthalpy changes, a Hess cycle can be used to calculate enthalpy changes of combustion or enthalpy changes of reaction using enthalpy change of formation data. So this is using enthalpy change of formation data. For example, with the combustion of methane, so combustion of methane is CH4 plus 2 O2 goes to make CO2, plus 2 H2O. That's combustion of methane. If I'm given enthalpy of formation data, I can calculate this enthalpy change of combustion amount. But enthalpy change of formation, definition of formation is that you're forming a product. You're forming 1 mole of a product, which means my arrow must be going towards the thing that I've been given enthalpy of formation for. So I will start with my, not start, that's a bad way of describing it. I will put my elements in their constituent states and amounts at the bottom of my Hess cycle, usually. If you're really comfortable with Hess cycles, you actually can draw a Hess cycle anyway, any which way round, and it won't matter. But especially to begin with, I would try and keep your Hess cycles a little bit more uniform, just to make it easier for you to kind of see the links and understand them. So I've been given enthalpy of formation data, I can put the elements at the bottom. That means my arrows must go from those elements to the thing that they are forming. So in this case, must always go up. That means I'm going to have some information for the formation of the reactants and some information for the formation of the products. So the delta HF arrow will, in this case, will point up. It always points towards the thing it is forming. The thing that is forming. Because that's the definition of enthalpy of formation. How do I work out what enthalpy of combustion is in this case, what the arrow across the top is? Well, I will start with my reactants. My arrow starts at the reactants and ends at the products. That's the direction that arrow is going. So I must start at the beginning of the arrow and end at the end of the arrow. I must start at the reactants and end at the product. I can't go the other way. I can't start with my reactants and end at the products because that amount is not going to be the same number. It will be the wrong sign in the end. So I must make sure that my process is representing the correct direction. So I'm going starting at the beginning, ending at the end. That means I'm going against the first arrow. I'm going against the first arrow. That means whatever value I have for delta F1, whatever value that is, I'm going to need to switch the sign on it or minus it. If I'm going with this arrow, I can just add whatever that value is. So my enthalpy change of combustion can be or is equal to minus whatever that value is, delta F1H, plus whatever that value is, delta F2H, and I've run out of space. Minus the first one plus the second one. And I've put it in brackets because I like to put it in brackets initially, because sometimes that value that you're given there is a negative. If that value is negative, let's say it's a value X, then you've got minus a minus. If you've got minus a minus, it's actually technically a plus. Okay, so what I would then do is resolve any issues between pluses and minuses and then plug it into my calculator. Don't plug this equation into your calculator because you'll put brackets in and you'll force the calculator to do something it doesn't want to do. So resolve the pluses and minuses and then plug it into your calculator. We're going to do an example of these in a minute. So what about if we've got other data? What happens if we've got combustion data, for example? So a Hess cycle can also be used to calculate enthalpy change of formation using combustion data. So for example, formation of methane. So formation of methane, if that's the thing I'm looking to calculate or looking to determine, again, normally we would put it across the top. It just makes it easier to see and it's a bit more kind of uniform then. You don't have to. Again, if you get comfortable, you can draw a Hess cycle however which way around you want. As long as the arrows are pointing in the right direction, it will be correct. But because I'm trying to determine enthalpy change of formation, I'm going to put that across the top. And the combustion data I've got, enthalpy change of combustion, the definition is the combustion of 1 mole of a substance undergoing complete combustion. So my arrow must go towards my combustion products. Now, combustion of carbon is going to produce carbon dioxide. Combustion of hydrogen is going to produce water. So my combustion products are carbon dioxide and water. And funnily enough, combustion products of methane are also carbon dioxide and water. Hence, I'm going to put carbon dioxide and water at the bottom of my Hess cycle so that both of those arrows are pointing towards those combustion products, because that's the definition of combustion, is the production of those things. And that is what that number is representing. That downwards arrow is what that number is representing. So combustion arrows, if you set up your Hess cycle like this, point downwards or towards combustion products. Towards combustion products. So how do I use a Hess cycle to work out what the enthalpy of formation is here? Well, I want to find out that arrow. So I need to start at the start of the arrow and end at the end of the arrow, because that's the process I'm trying to work out. So it will have to go that way. Let's make that a little bit neater. Let's go like that. There we go. That means I'm going with this first arrow. So that's the value that I've been given there is correct. But I'm going against this arrow now. So the value I've been given there, I need to switch the sign of, or I need to minus it. Now, I would recommend just minusing ones you go against and adding ones you go with, because it'll make it a lot easier than trying to change numbers and then forgetting if you have or haven't changed the sign, etc. So I would just put it together in an equation, resolve the pluses and minuses in your equation, and then plug it into your calculator like that. I think there's less chance to make a mistake. So what am I doing here? This is delta HF. Or delta FH, I should say. That's the enthalpy of formation, and it's made up by adding delta C1, the combustion of that first arrow, and minusing, because I'm going against whatever that second arrow is. And I could put them in brackets. I can then resolve the signs. If I've got any minuses or plus minuses, I can resolve those and then plug it into my calculator.